brief video just to introduce the idea of surface area in terms of how we use an integral to find the surface area of a three-dimensional object. So I'd like to begin with kind of an easy one that we're kind of familiar with, the idea of a cylinder. So let's say we have the x and the y axis here, and we just take some function, some constant function, we'll call it y equals c. All right, and if we just rotate it around the x-axis, all right, we end up with a cylinder. And the question is, how do we find the surface area of a cylinder? So this is an idea that we're kind of already familiar with. So one way to think of this is, I know there are formulas and you're probably familiar with them, but I just want to go over this simple example to kind of motivate how we would do it when we don't have a constant function like this, when we have a function that's curved. So one way to think about this is I can take a slice or kind of a band from the middle of this thing. All right, so we kind of take this piece out, and notice it's hollow, right? It's not a disc. It's like a slice, that has some thickness to it, kind of a band that we can take it out of here, and then we can unfold it. All right. So if we kind of take this, if we just kind of maybe cut it, say right there, and unfold it, we get something. We get this band that looks like a rectangle. All right. So if we can figure out what the lengths of these two sides are of this rectangle, then we would have the surface area of this piece right here, and then we could just add up all the surface areas along our entire cylinder to get the surface area of the cylinder. And in this case, this is, this isn't open. There's no ends on it, so we don't have to worry about the surface area on the end. All right, so let's first think about the distance around. Well, that's just the circumference, right? So the formula so if we kind of cut this and unfolded it this way, then the circumference would be the long side, and that would be 2 pi r. But notice y equals c, that actually is our radius. So so it's actually 2 pi c, whatever this constant is, that's what our radius is. And along here, we can just call that L, but that's just kind of the length, right? So it's just a slice, so this would be a slice of length L, and so the area then would be 2 pi c times L. All right, and then we would add all those up. That's kind of our summation notation to say that we would add all of those up. Now, let's look at an example that's not a cylinder, all right, and kind of extend that idea. So let's say we have, I don't know, something that it's more curved, all right, so this is some function f of x, looks like it maybe could be square root or something like that. But nonetheless, we have this curve, and we are going to rotate it around. We have kind of the curve reflected here below the x-axis, and again, remember, this is hollow. We're just thinking about the area on the outside of this. All right. So again, we use kind of the same idea. We cut a band in this thing, something like this, and remember it's hollow, so it's just kind of this band that runs around it, right? Okay, so again, we're going to cut this, and notice that it's going to be very similar, right? What's our radius? Well, the radius for any of these slices is going to be the function value. That will give us the radius. What about, and this is where it might be useful to use another color, what about along here? How do we get that? So let me first, let's unravel this. We cut it here, we unroll it. And in this case, it's actually going to be a little bit curved. So bear with me. I'm just going to forget that it's curved and kind of draw something like we had before. But notice, these ends aren't flat. They're curved, all right? But we've already said that the circumference, or kind of the length of this strip or this band, is going to be 2 pi times whatever the function value is, because the function value at any point along here, right? We might have another one here that we cut out, right? We could have another one down here, but no matter where I am on this thing, my radius is the function value. We saw this idea when we were looking at the Methodist cylindrical cells and we were revolving around the y-axis. The question still remains, though, right here. What are we going to do with that? So if you remember here, we just called it L, and it was just, we could just kind of take whatever the difference in the x values are. How do we find the length of this piece right here? Well, we just talked about arc length. This whole thing along here is the arc length. We have figured out, right? So we know that the arc length, this whole arc length along here, we can find that by taking the square root of 1 plus the derivative of the function squared. So we could also do it for any little piece, right? That would be this length right here. All right. So for any individual strip, then we know that the area, and we're going to call it surface area, is going to be 2 pi times the function times the square root of 1 plus the derivative of the function squared. All right, that's for any individual band or slice, and then we add them all up. And what we've learned, if we've learned nothing else in this course, we've learned that when we add up a bunch of these and we let these widths go to 0, we end up with, so let's say right here, the middle of our, from here to here, if we call this point down here A on the x-axis and this point right here B, then what we end up with is an integral from A to B of all of these, right? All these little strips. So 2 pi times the function, that gives us this piece, and then the length is given by the arc length, 1 plus the derivative of the function squared. All right, so that's our formula. It can be simplified. The 2 pi obviously is a constant. That can come out. So it just simplifies to this. Okay, so now let's just look at one quick application, of how we might use this formula. So I want to take a look at if we were given the function y equals e to the x, and we want to know if we take that curve. Let's draw that curve first. All right. So at 0, e to the x is, we want to look at along 0 to 1. So we take that curve. So first let's draw that curve. So at 0, it's at 1, and then at 1, it's at e, which is about 2.718. So let's just approximate here. So if it's 3, then it's going to be a little bit less than 3. So say something like this, and we know it curves upwards. So there's our curve along 0, 1. So if we rotate this around the x-axis, we're going to have something that's symmetric with the x-axis, right? So we can kind of draw the same thing down here, maybe go into about right here, and it's like this, right? And then we rotate this thing around, so we end up with, something that kind of looks like a horn, all right? Again, it's empty, it's not a solid, all right? So this is, now again, we're just looking for the outside part here. How do we get the surface area of this surface that results when we rotate the curve around the x-axis? Okay, so we know the surface area, we know the formula, just see it again, right? And in this case, we know our bounds are going to be 0 to 1 because that's what we have right here. And actually, I'll go ahead and put the function value. It's going to be e to the x, right? Square root of 1 plus the derivative squared. So the derivative, of course, of e to the x is e to the x. That was easy. All right, and then we want to square that, so that's e to the x squared. And anytime we have the power raised to a power, we multiply, right? So that is e to the 2x. So e to the 2x, all right, dx. Now, similar with, there are ways to do this by hand, but it gets pretty messy. So what I would suggest is that you use your calculator. Just be careful putting these things in, that you put them in correctly. And if you do that, so for this piece right here, for this integral, you would get 3.65. You multiply that by 2 pi, right? And you would get something that's about 22.94. All right, so that's just an example of how you would use the surface area formula to find the surface that results when you take a curve and revolve it around the x-axis.